Welcome to Study Loop.
Okay, so we know magnetic field B can be equal to mu 0 times n times IA squared over 2 times x squared plus a squared to the power of 3 over 2. Mu 0 is the permeability constant. N is the number of turns in each coil. I is the currents in a wire, and A is the distance between two coils. And we know x is the distance from the center of the coils to the points where the magnetic field to be determined. Okay, so therefore we have BL, which is the magnetic field at the distance x plus a over 2 due to left coil is equal to mu 0 times nia squared over 2 times x plus a over 2 to the power of 2 plus a squared to the power of 3 over 2. And BR is the magnetic field at a distance x minus a over 2 due to right coil, which is equal to mu 0 nia squared over 2 times x minus a over 2 to the power of 2 plus a squared to the power of 3 over 2. So now we can determine the total magnetic field in this case, which is equal to BL plus BR. And if we do some arrangement here, eventually we have magnetic field is equal to mu 0 times nia squared over 2, and then times 1 over x plus a over 2 squared plus a squared to the power of 3 over 2 plus 1 over x minus a to the power of 2 plus a squared to the power of 3 over 2. And for question B, this is the B versus X graph, okay? Range from 0 to A over 2. And then you can use this graph to compare with the graph for the magnetic field due to the right-hand coil alone, okay? And for question C, well, at point P, we know X is equal to 0. So therefore, remember, so now we can just plug in the X is equal to 0 back into the equation. Therefore, we have the magnetic field B is equal to mu 0 nia squared over 2 times 1 over 0 plus a over 2 squared plus a squared, and then to the power of 3 over 2 plus 1 over 0 plus not 0 plus 0 minus, okay, 0 minus a over 2 squared plus a squared to the power of 3 over 2. Oop. And this will give us the magnetic field can be equal to mu 0 nia squared over 2 times 2 over 5a squared over 4, and then to the power of 3 over 2, which will give us mu 0 nia squared over 2 times 2 over 5 over 4 to the power of 3 over 2 times a cube. And as you can tell, 2 can be cancelled out, a squared can be cancelled out, and this will give us b is just simply equal to 4 over 5 to the power of 3 over 2 times mu 0 ni over a. Okay, so for the next question, well, we just simply plug in the values back into the expression we just determined. So we have magnetic field at point P is just simply equal to 4 pi. You know what, let's do the fraction first. So it's 4 over 5 to the power of 3 over 2 times 4 pi times 10 to the power of -7 Tesla times meter per ampere, then times 300, then times 6.00 ampere over 0.08 meter. Okay, since 8 centimeter is equal to 0.08 meter, and this will give us the magnetic field is about 0.02 Tesla. And for the last question, well, we know at point P, x is equal to 0. Okay, and we know the magnetic field at point P is equal to mu 0 nia. No, sorry, not nia. My bad. Let me see. It's 4 over 5 to the power of 3 over 2 times mu 0 ni over a. And as you can tell, it has nothing to do with x. So therefore, dB dx at this point should be equal to 0. Okay, since it has nothing to do with x in the equation. Same for the second derivative as well. Okay, so dB squared over d. Let me see, it's d squared b. Sorry about it. D squared b over dx squared should be equal to 0 as well, since the first derivative is equal to 0 already. Okay, so this shows us that the both first derivative and the second derivative of the magnetic field is equal to 0, which means that the fields change very slowly. Okay, so the magnetic field change very slowly. Okay, so let me see, change very slowly. And this is the answer for this question.